All right, so now that we have a basic understanding of how light works, then we're going to move on to the kind of some important conclusions that were drawn from the quantum mechanical model of the atom based on some of the empirical observations. So what you're going to be doing in lab this week is you're going to observe that you can have a Bunsen burner, or in this case a Terrell burner, and on this burner you're going to have a lovely flame, right? So what we're going to do is we're then going to take a sample of some kind of powder, and when we place this powder into the flame, we'll see that the flame actually changes color. And we'll observe that some flames can burn purple, some flames can burn green, some flames can burn all kinds of really interesting setups whenever you introduce this sample into your flame. So what happens is when they took a look at the light that came off of this, they took the light from this flame, passed it through a narrow slit, and so we would see our beam of light coming off in a very focused way, pass it through a prism. What ended up happening is we would see these unique lines that would come out of all kinds of different colors. And what's really interesting is that each atom or each element has its own unique emission spectrum, which is what we looked at here. And so we'd see our light separated into different colors once we passed it through that prism. And since each element had this same type of spectroscopy, there was a Swedish chemist by the name of a whole bunch of atomic spectra in each different element. And he came up with kind of an empirical observation. So he said that each element's emission is unique. And so he said that the wavelength of light that comes off is equal to some constant times 1 over m squared minus 1 over n squared. And so with this, this is what was called the Rydberg Equation. And in this, there are a couple important variables here. The Rydberg constant, which is that capital R, is equal to 1.097 times 10 to the 7th inverse meters. He also noted that m and n are integers of each other, or integers. So in this case, they had to be something that had a whole number to it, whether it was positive or negative. And this was kind of a breakthrough at the time because they couldn't figure out why each element's emission spectrum was so unique. And this was the first breakthrough that said, okay, here's what happens, and this is the empirical observation based on the data. And so once we started getting a little bit later on in the century, kind of around like probably the 1930s, 1940s, there was a scientist by the name of Niels Bohr. And he said, hey, I think that these integers are actually specific energy levels. So when we took a look at each of these different spectra, he pieced all of this together to say, I think that Rutherford's model was pretty good, but we can add a more complete picture. We're only going to draw half of the atom here. But he said, I think that within the electron cloud of our atom, that little dot in the middle is our nucleus, I think what's happening is there are these specific transitions that are occurring in the electrons. So that instead of saying the electrons are all over the place, he said, I think the electrons can only be in certain spots. And the colors that we observe are the electrons moving from higher energy levels to lower energy levels. And it turns out that this worked out really well because he could calculate the distance between these energy values. Oh, sorry, wrong one. That's a 3 to 2. And so he said, I think these individual levels are going to be where we can find these electrons. And we'll call these energy levels principal energy levels. And so what happens is he said, okay, so like here's the jump that's happening, right? We have our electron, maybe that's hanging out in this first energy level. This is in the ground state. This is normal before we put it in the flame. He thinks when we add the flame, they absorb the energy and jump to a higher energy level. And so now they've been excited into a state that n equals 5. And then once they leave the flame, once they leave the energy is released as they come back down. And this relaxation is what releases each different color. So as it moves, it excites when it's inside the flame, and when it leaves the flame, it comes back down. So this was kind of a really big deal at the time because this provided the first tangible, mathematically correct explanation of why Rydberg was correct. So Bohr said, I think that these electrons aren't necessarily in this willy-nilly cloud. I think that these stationary states or these orbits of the electrons are actually very specific. And we can only see electrons in certain locations around the atom. And these locations, or these orbits of our electrons, we call energy levels. And so we'll see most of our electrons can only be here, in the second ring, and work its way out. And this is kind of a really big deal. And so remember, energy is excited in the flame. You see that excitation, and as it relaxes back down, we observe that energy is released in the form of light, or in this case, as a particular color. The other thing that was really important is that Niels Bohr said, I think the size of the jump or in this case, the size of the relaxation determines the color. And when he plugged this in, he found out that this was actually correct because this transition between the 2 to 3 level gave off red light with a wavelength of 657 nanometers. When he looked at this transition between 4 to 2, he saw that this gave off 486 nanometers in like a greenish blue light. And in this last one, this one gave an emission of 434 nanometers, where we had this blue light. So remember, as we're decreasing or as we're increasing wavelength, we decrease energy, right? So the higher wavelengths mean lower energy. That's what we talked about in the last video. And this makes sense then. So in this case, my lowest wavelengths, my blues and purples, actually have the highest energy photons that are released. And so there's a unique way that each of these can be used to identify an element. And this is how a lot of chemists back in the day would determine what kind of elements you had inside your compound. So if you were looking for poisons like arsenic, you would see them actually put the sample of it in the flame and look for the particular wavelength that corresponds to the presence of arsenic inside the sample. So now there was this first quantum mechanical model of the atom where these electrons can only live in certain energy levels. This was kind of a big breakthrough. And there was a lot more studies, and there were way more studies that went into it. So in this case, what they started looking at now, this The next scientist to take a big look at this was a scientist by the name of Broglie. And Broglie actually had a really cool thesis at the time when he was going to defend his PhD, and he proposed this idea and was originally shot down. It wasn't until about 4 or 5 years later when Albert Einstein got a hold of his work, he called up those university folks and were like, "You guys are idiots. This is brilliant. Give him his PhD." And so he was actually retroactively awarded his PhD. But he said, when we take a look at an electron moving through space, it has some kind of wave nature to it. And so the wavelength should be tied to its kinetic energy. So in this case, he said, well, I think we can then relate the wavelength of our light to Planck's constant over mass times the velocity. And this was a pretty big deal at the time, because he said you can determine how fast an electron's moving based on its velocity. And so some important things here are that, again, lambda in this equation is our wavelength. We'll see h is Planck's constant, that's 6.626 times 10 to the negative 34th joule seconds. M is the mass of an electron. And in this case, the mass of our electron comes out to be 9.11 times 10 to the negative 31 kilograms. And then V is the velocity of the electron in meters per second. And so de Broglie figured out that you can use the wavelength or the velocity to determine what the wavelength would be. So in this case, let's take a look. Determine the velocity of an electron whose light has a wavelength of 2.74 angstroms. And so with angstrom in this case, it's the same thing as saying 10 to the negative 10th meters. So what we can do is we can set this up. We know that I have my wavelength here is 2.74 times 10 to the negative 10th meters. And that's going to be equal to 6.626 times 10 to the negative 34th joule seconds over the mass of one electron, 9.11 times 10 to the negative 31 kilograms, times velocity. So what I would do is I would flip-flop my equation and rewrite it as such. So then let's take a look and see what this math would come out to be. All right, so when we plug all of these values in, we end up to see that the velocity of this electron is actually incredibly fast. It's moving at 2.65 times 10 to the 6th meters per second. So de Broglie lets us figure out the velocity. However, there was kind of then this disagreement that came up. When we took a look at these, Heisenberg ended up saying, okay, we can either know the position or its velocity. And so Heisenberg's uncertainty principle kind of put a little bit of a limit on our understanding of the quantum mechanical model. And he said you can know either the position or the wavelength, but you can't know both. And so what he said is, by measuring the uncertainty, you can kind of figure out some important pieces. But in this case, you can know the change in x, or in this case, the change in position, times the mass times the change in velocity should be greater than or equal to h over 4 pi. And so what this says is that the product of the uncertainty in position, in this case, the delta x, and the velocity must be greater than or equal to a finite number. And this finite number took a lot of work to figure out what it is. In this case, it's Planck's constant over 4 pi. So you can know the position, or the more you know about the position, the less you know about the velocity. The more you know about the velocity, the less you know about the position. And this is due to the wave-particle duality of light. In this case, the properties that let it behave like a wave and the properties let it behave like a particle. Because of that, you can't know both. You can only know one. All right, so then a few other important pieces to go into before we jump into our last little bit about electronic structure is an introduction to the fact that we're going to have to do a slight revision based on this new uncertainty. So earlier, we drew a picture that showed, hey, here's our atom, here's the nucleus, here's this idea that we have these orbits that are very finite. It turns out that these orbits are actually a little bit fuzzier than that, because of this probability and uncertainty. And so this just means that this is where these regions are the highest probability of finding an electron, which kind of is just a small modification to our Bohr model as originally described. So in this case, these are the places electrons are most likely found. And you can often hear this called, in a fancy word, as a probability density. This is the place we're most likely to find it, and it gets less probable the farther away we get from these particular places. All right, we got one more video coming up about the quantum mechanic model of the atom and how we can put all of this together to kind of provide the foundation that we're going to use to organize our electrons inside this cloud.